or not. After JFET, the fourth topic, which will be covered in your midterm, is op-amp. Hence, today we'll talk again about the op-amp. We won't be solving problems just like we did in regular class. However, I would like this session to be interactive so that we can discuss back and forth and make sure you have properly understood the concept. I'm at slide number 2 now. Again, this slide should read the basic differential amplifier. What are the characteristics of a differential amplifier? You will have 2 inputs. You can also have 2 outputs. Sometimes you have 2 input pins and just 1 output. That is also based on the differential amplifier, which is the op-amp. On the screen shown on the left-hand side is one of the very common differential amplifier circuits used in electronics. It is based on 2 BJTs, as you can see, Q1 and Q2, also in a common emitter connection, where emitter is common to both input and output. These 2 amplifiers also, you can tell, these are NPN transistors. The inputs are base. You have the base 1 and base 2. 2 outputs are taken at the collector of each amplifier. You can have more than 1 biasing. In this case, you have VCC, which is common, and then you can have VEE. Sometimes you might even have ground. But this is the basic idea of a differential amplifier. You can have 3 input modes of a basic differential amplifier. What are these modes? Can someone remember the input modes of basic differential amplifier? I'm talking about the input, not the output.
There are 3 of them, right?
3 of them. What are the names?
First base. Is it base?
No, it has to do with how you use the input pins. Single-ended, double-ended, and common mode. What do you do in the single-ended input? One input is connected with some signal. The other one input is ground. That's single-ended. What do you do in the double-ended case?
Both pins are connected to 2 different signals.
2 different signals. Are they in the same polarity? Or double-ended?
I believe they're opposite.
They should be in the opposite. And the last one is the common mode input. What do we do in the common mode input?
Both pins connected to the same signal?
Exactly same signal. Use a common connection, exactly same signal, which means same polarity. However, one of the input pins are plus and the other one is a minus. So when you take the same peak, one is plus, one is minus, theoretically the output should cancel out and you would have no output for the common mode. The common mode output ideally is 0, but practically in reality there'll be a little bit of output. It cannot completely reject the common mode input. That's why there is one parameter in the op-amp which is very important. It's called CMRR, common mode rejection ratio. And most of the common mode input is due to the noise. So if you have a high CMRR value, high rejection ratio, which means the amplifier is quite good at suppressing noise. This one is a basic op-amp. Now the title is correct. It is the previous one is basic differential amp. This is basic op amp. In the circuit, this is the symbol of an op amp. We are showing inverting input and non-inverting input. So one is minus, the other one is plus. By practice, some people draw the minus pin on top always and plus pin on the ground. I have seen only few cases where the plus pin is on top and the minus pin on the ground, on the bottom, but it doesn't really matter as long as you do not make mistake in the fundamentals and the output is taken from only one pin. It's a very high gain differential amplifier. So this is belonging to the family of differential amplifier. It's one type of differential amplifier. On the input side, there's a very high impedance, typically in mega ohms. When you have mega ohms, several mega ohms, it is almost like an open circuit, which means if you provide any input on the pin, either plus or minus, there is no transfer of current through the body of the op amp. There is no current going from minus to plus. On the output side, you have low impedance, less than 100 ohm. If you do not connect the output with any input, it is called the open loop operation. In the open loop operation, the gain can be 5 digits, maybe 10,000, 20, 50. So there are 5 digits in the gain. But this is not a stable operation, not completely linear. Also, when you operate the op amp in open loop, you really do not have much bandwidth to operate. The available bandwidth, the frequency bandwidth is much less. So what typically is done? Connect the output with an input side. It is called closed loop. In a closed loop operation, the gain will go down a lot. You won't have 20,000 gain. You might have 3, 5, 10, 20. You might think you're losing something here, but the gain or the plus side is you will have a very wide range of frequency band in which the op amp will operate. The response will be linear, will not be distorted, and it will be more stable gain. This is the one I was talking about, CMRR, common mode rejection ratio. So far, we have known that the op amp, it has two inputs, which are opposed phase. So inverting is minus, non-inverting is plus. If you have a signal that is common to both inputs because of this opposing phase, 180-degree opposition, it will be cancelled out. Common mode rejection ratio is the ability to cancel out common mode signals. Again, it is not a common practice to connect both pins with the same input. Usually we provide two different inputs and maybe one single-ended. So what is common to both pins? There are two things. One is called signal, the other one is called noise. Signal is the one that you desire. Let's say you have a sine wave input, that is your signal. You want the sine wave to be amplified properly. But if there is harmonics in the signal, let's say it's not purely sinusoidal or second, third, fourth components of the basic frequency, that is unwanted. Any unwanted signal is called noise. What are some of the examples of noise? In real life, can you give me examples of noisy signal?
The static you hear.
Yes, static, yes, that's one kind of noise. We operate so many devices. You have cell phone, you have microwave. In the hospital, you have devices that measure heart rate, blood pressure, all the vitals. They all get affected by the devices around. So your cell phone reception, your signal might be affected. If you are running a microwave in your home and you are close by, it might be affected. There's actually a way of measuring that using a software called LabVIEW and some measurement equipment. Anyways, the noise is something that you don't want. For both inputs, noise is common. They can go to both sides. That's why in the common mode, we want to reject them. You can express CMRR in terms of just a ratio or a ratio multiplied by 20 times log of base 10. If you just take AD over AC, you get a number without a unit. And then if you multiply this ratio by 20 log 10, the unit has to be in decibels. What is again AD and AC? AD is the gain in differential mode. Let's say in differential mode you have input 1 volt and output 10 volts. Your differential gain is 10. And then in common mode, if your input voltage is 1 volt or 10 millivolt and your output voltage is, let's say, 15 millivolt, you have a common mode gain of 1.5. If you look at the equation on the bottom right hand side, V out, this is the output equation of the op amp. AD, the thing in the bracket, V plus minus V minus is VD. So in the differential mode, you see what is provided in the plus pin, what is provided in the minus pin. If you have 2 volts in the plus pin and negative 2 volt on the minus pin, 2 minus negative 2 becomes 4. VD is 4. AD, VD, that's differential voltage, plus AC times VC, common mode. Common mode voltage is the plus pin voltage plus the minus pin voltage divided by 2. If both values are the same, 2 and minus 2, you will actually get 0 VC. 1 plus, no, not 0. 2 plus 2, 2 plus minus 2, yes, 0. Or you can say 0.5 and then negative 0.5. If you use a negative 1, you'll get 0. The way of writing is AD/VD plus AC/VC, but you still need to know what is VD. If I give you a circuit, how do you calculate the differential voltage? Always use V plus minus V minus. Take the plus pin voltage, subtract the minus pin. Do not do the other way. The other way will be wrong. And for common mode, it's easy. You just add the 2 voltage divided by 2. That's the common mode voltage, VC. We talked about the gain, open loop versus closed loop. Open loop gain is usually 5 digits. Closed loop gain is a few units. And closed loop gain will always be lower than the open loop gain. So the feedback we provide from the output side back to the input side, it's a negative feedback, especially when you're inputting using the inverting pin. It will reduce your gain, but many characteristics of the op amp will be improved. One of those is frequency response, linearity, and stability. Here's an inverting op amp. You can see it is a single-ended input. One of the pin is receiving the input, the other pin is grounded. So this is one of the input operations. We are providing this to the minus pin. That is why it is called the inverting op amp. What are the two assumptions that we make when we calculate or derive equations for the op amp? Can someone remember?
What do you ask again, please?
The two basic assumptions for solving op amp problems. It is not on the slide, but it was talked about in the class.
It's not inverting, right?
Sorry,
Is it inverting or it does not?
this one is an inverting pin. It doesn't matter. It doesn't matter what type of op amp you use. For all op amp, there are two basic assumptions. What are these assumptions? It's like I wouldn't say it's an equation. For example, in the case of JFET, we assume that gate current IG is 0 always. So what are the assumptions for op amp?
The current going into the op amp is always 0.
The current in the op amp is 0, means there is really no current. You can say that if you have a source like this, it will not enter the op amp. It will go away from the op amp using your feedback connection. So no current goes to the op amp. Your statement is correct. First, I didn't understand it. You can say it's very high input impedance, no current goes to the op amp. What is the second assumption? When you try to solve problem or derive an equation, what is the second assumption?
Maybe what VI connect to it will be like the VR will be that value, like it's connected to negative, VR will be negative too. If it's positive, the VR will positive too. Is that what you're looking for?
That's for inverting. No, that's not what I'm looking for. That's for inverting. If I put non-inverting, there will be no change of sign. The second assumption is V plus equals V minus always. The voltage at plus pin and the voltage at minus pin, they are the same. So what is V plus here? You can see what is V plus.
Grounded.
Grounded is 0. So we have to also set V minus equals 0. If this is 0 and this is 0, it will make you think that there is a short circuit. If there's a short circuit from minus to plus, there's a connection and there's a current, but this is just a virtual concept. In reality, there is no short circuit. That's why it's called a virtual ground. So you can derive the equation. We derive the equation for the inverting op amp. We say V plus equals V minus. Also I1, if we call this current I1 and we call this current IF, I1 equals IF. The equation of I1 is what? Ohm's law. V1 minus V minus, which is 0, V1 over R1 equals 0. From here is IF. V minus minus V out. 0 minus V out over RF. So you see the equation becomes V1 over R1 equals minus V out over RF. So you see the gain V out over V1, or V1 equals minus RF over R1 times V out. It's a minus sign. Whatever you put inside, it's multiplied by the gain and the sign is flipped. This is for inverting. It provides a negative feedback. From the output back to the input, it provides a negative feedback. The gain is less than the open loop gain, but it stabilizes the operation. So this is what I told you. Gain is V out over V in, negative RF over R1. If both of them are the same value of resistor, you have a gain of 1. We call it the unity gain. When the magnitude of the gain is 1, it is called the unity gain amplifier. And obviously with the negative sign, it tells you that there's a phase shift of 180 degrees. Here's the virtual ground concept I used to explain in the class using two different values of voltage. So V1 is the voltage at the input side. It is not the V minus voltage. V minus voltage is here, small Vi, in between R1 and RF. You can see in between R1 and RF. We compared maybe half millivolt of Vi with a 1 volt or 2 volts of V1. If you compare that, Vi almost close to zero. This concept makes people think that there's a ground, there's a short circuit. But actually there is no short circuit. The ground is virtual. It's a conceptual ground. Because of the high input impedance, normally you think that when you have a short circuit, all current goes there. So all current would go to the plus pin, which is not correct. High input impedance forces all the input current through the input resistor and the output feedback resistor. We studied a few types of op-amp circuits. The first one, inverting op-amp, and non-inverting is the second one. You have seen how to derive the inverting op-amp. What about the non-inverting? In the non-inverting op-amp, this is how the connection is added. A direct connection to the plus pin, and on the minus pin, the resistors are connected. You can set V plus equals V minus. Here V plus is V1. And what is V minus? At that node, what is V minus? It's not zero. What is it? Let me point out the location. At this point, you can measure V minus. You can see the surrounding network and try to guess what is V minus.
Is it equal to the inverting?
Non-inverting is V1. And what is in the inverting pin? V1 equals V minus, sure. But also you can express V minus in a different way. V minus is not zero, it is not grounded exactly. It's connected to the output side using two resistors. What do we call this circuit connection? It's called the voltage divider. It is V out R1 divided by R1 plus RF. That's the voltage at this point. This equals V1 because V minus equals V plus. And then you rearrange the equation, you will get an expression, the formula for the non-inverting amplifier. V out is V1 multiplied by 1 plus RF over R1. There's another connection known as unity follower. You want the input exactly to be same as the output, or output same as input. You don't want any change in sign. This is the connection. Put a V1 on the plus side, and the output side you connect with the minus pin. V plus equals V minus, so V minus is V1, V out is V1. This is an important one, summing op-amp. Because the op-amp has very high input impedance, if you have multiple inputs at any pin, you can treat them separately and then add up later on. Here's an example of an inverting summing op-amp. You have three inputs coming to the input pin. These are parallel inputs, not series, three parallel inputs. Each one V1, V2, V3. If you ignore V2 and V3 and just focus on V1, the output is minus RF over R1 times V1. Now you ignore V1 and V3, focus on V2. the output is minus Rf over R2 times V2, and the third one, ignoring the first two, the output will be minus Rf over R3 times V3. And then you all add them together. You can take the minus sign out of the bracket. This is the form of equation. It is not limited to just 3 or 2 inputs. You can have many inputs. They will all be treated separately. If you are given an equation of an op-amp with 2 or more parameters, it is a summing op-amp where you have more than one inputs to add. Integrator. An integrator is an op-amp where the input side you have a resistor and on the output side you have a capacitor. It is also part of a filtering circuit. You can use low pass, high pass with integrator and differentiator. When you have the capacitor as a feedback element and resistor as the input element, the output functions like an integral of the input. So let's say you have a time function input. The output also is a time function. It's going to be minus 1 over RC. Minus is due to the fact that it is an inverting pin. And then multiply that by integral of your input. So here input is V1 of t. You have to integrate V1t dt. If it is a function of x, it would be V1 of x dx integral. To solve this type of problem, you should remember the calculus, integral calculus and differential calculus for the differentiator. This configuration is used in low pass filter. So low frequency will pass, high frequency will be cut off. Pick the position of capacitor and resistor. You will get a differentiator. The output is a differential equation. Minus, again, minus sign for the inverting pin. Minus RC times dV over dt. We are assuming V is a function of t. V1t, so dV1 of t over dt. This one is used in high pass filter circuit. Filter circuits are taught at the end of this chapter. What's a high pass filter? The low frequencies will not pass through, but once you reach the lower cutoff frequency, then the high frequency will start showing up and you will have the output. This is a high pass filter. Here is one problem which we did in the class. The output voltage is given for an op-amp, so it is asking you to design. You need output as half sine x plus 2x squared minus 4. Input has to be given, otherwise you don't know what to do. Allowed inputs are cosine x, x and 1 volt. You can see how you get sine x out of cosine x. If you take d dx of cosine x, it's negative sine x, and then you have to go through one more inverting stage to make it positive. So on the input side where cosine x is connected, you need a differentiator. Put capacitor first and resistor later. How can you get a term x squared from an input x? You cannot do d dx of x, that will be 1. If you want to change x into x squared, the mathematical operation is differential calculus. You have to integral calculus. You have to take integration of x dx. Integration of x dx is x squared divided by 2. Somehow you have to change it into 2x squared. You can do it either on the input side by picking proper resistor and capacitor, or you can just get x squared over 2 and then deal with it later on in the output stage. But the design problem may have some constraints. Maybe I will just allow you to use only certain value of capacitor, and I might make some restrictions on the output side that you cannot use anything other than these values. And finally, for plus 1 volt, you have to change it to minus 4. How can you change it to minus 4? You can directly actually put the 1 volt input with a resistor, and then on the final summing stage you can take a resistor 4 times the input resistor. You will be fine. But the way we did in the class, we put an additional op-amp stage in the beginning with the gain of 4, and then on the output side we did unity gain system. So RF and R1, R2, R3 all were the same. The problem, this is the one we did in the class. It's a summing op-amp. On the input side, you see 2 inputs are coming. You have a V2 and then you have a V1 multiplied by 10. It will be multiplied by negative 10 because you have an inverting op-amp. So you have 12 millivolt. The feedback resistor is 10 times the input one. You will have minus 120 millivolt coming in. And then again, here's a 10 times gain. Minus and minus will become plus. You will have 1200 millivolt. Well, 1.2 volt. And then you add something else. 18 millivolt times 10 and negative 1200 millivolt minus 180 millivolt. I think it's 1.02 volts. That is your final output. Any question about this circuit? No questions? We talked about frequency parameters in the class. So 2 parameters, gain and slew rate. Slew rate is the rate of changing. Let's talk about gain first. This is a picture of gain versus bandwidth. Where are you going to get the maximum gain? A sub BD.
Peak?
Yes?
No, I answer your question. Where do you gain? So I said the peak.
The peak. This is the peak. This is your maximum gain, but it happens at an open loop. It is often determined or denoted by A sub OL or ABD. From here to here, this is a frequency log scale. There is not much bandwidth available. Not very useful. Once you close the loop by connecting the output with an input, the gain will rapidly decline. Maybe this is the center cutoff frequency. But around the frequency, you will have spaces in the frequency band to operate. Let's say you are operating at this frequency FC, you're gonna get 0.707 times the gain. I think it's decreased by 3 decibel. That's why it's called the 3 decibel point sometimes. When you close the loop and then you go to the cutoff frequency, your output decreased by 3 decibels. And as you keep increasing, if you want to increase the bandwidth, you will be losing the gain. Here the bandwidth is measured from the 0 frequency to whatever you have. If you have a log scale, this is basically typically base 10 log. So this one is a linear, this one is a log. 10, 100, 1000, 10,000, that's how the log scale works. No feedback resistor is what you have the top gain. Once you connect the feedback, it decreases. Slew rate is the maximum rate at which the op-amp can change output without distortion. What is the meaning of distortion? What do you understand by distortion?
Anything to affect the signal?
A distortion means corruption in the signal. Means, let's say you have a sine wave, and then the output does not look like a sine wave. It looks maybe crooked or something that you don't recognize. That's a distortion of the signal. It's a distorted signal. Now, the slew rate refers to a situation where the op-amp is changing output rapidly, but it's still keeping the same shape. So at the maximum rate at which it can keep doing that, it is called the slew rate. It is typically listed on the spec sheet, okay, in voltage per microsecond. If you try to change the output at a higher rate, what is going to happen? It cannot keep up. Unfortunately, it cannot keep up. So the signal will be distorted. Any questions? Okay, maybe no questions, right?
No.
All right, then let's move on to the next one. Next subtopic. And the slew rate is also important in determining the maximum signal frequency. Again, you have to keep in mind that we are using the slew rate and signal frequency. So as long as it does not distort the signal. So the slew rate also determines the maximum frequency of the op-amp without distortion. If you try to go above this frequency, signal will not keep its minimum shape. I mean basic shape. It is given by slew rate divided by 2 pi and Vp. Vp is the peak voltage. The frequency has to be less than or equal to this parameter, SR over 2 pi Vp. If it goes above that, then you are in trouble. That's the idea of the slew rate and maximum signal frequency. If you look at the spec sheet of an op-amp, you will find some typical values. They will give you some absolute voltage current rating, electrical characteristic performance. Here's one example. Supply voltage plus minus 22. Where is the minus coming from? There are two pins. One is V plus and not the V plus. V set plus V set, and another one is called negative V set. You can add supply voltage there. Set refers to saturation. After the midterm, we have a topic where you see comparator. There you see what happens with the V set and minus V set. Of course, just like any device, you have a limit of heat dissipation or power dissipation. In this case, 500 milliwatt or half watt. Differential input voltage, it refers to the limit of how much difference you can have on the differential input. When you calculate VD, you should not have more than plus minus 30 volt difference. And the input voltage itself should not exceed the magnitude of 15 volt on any given pin. Supply voltage and input voltage, they are not the same. What is the supply voltage? It is the DC biasing. Remember, without the DC biasing, the amplifier will not turn on and amplify signal. It was asked in the quiz. Electrical characteristics. This is a specific model of IC, op-amp IC, micro A741. You can see the typical maximum values and the units. CMRR, I'm specially I'm particularly looking at CMR. This is the first thing I look at. 90 decibel, the common mode rejection ratio, typically is 90 decibel. Power dissipation is also something I would look before I design any circuit or device. You can see it is maximum 85 milliwatts. What else do we have? Input resistance. Did you see the input resistance? 2 mega ohm. But what is the output resistance? Low output impedance, only 75. This is ohm. This one is mega, this one is just ohm. These are some performance graphs. If you, for example, increase the supply voltage at a higher VCC, you will get better voltage gain in decibels. But also the power consumption is going to go up. So there's a trade-off. You can get more gain with more VCC, but also the power consumption goes high. You might reach your limit. And this one, the bottom left graph is input resistance versus frequency. So at a higher frequency, how the input resistance behaves. The output resistance, typically you have high input impedance. Maybe after a certain cutoff frequency, the impedance becomes less, which means you are more subject to incoming noise. For the output resistance, you need low. This is in ohms. And after that certain cutoff frequency, it looks like the cutoff here is 10 kilo ohm, 10 kilohertz. The output resistance increases. Not a very good situation if you want a proper output. So cutoff frequency is what you need to be concerned about through calculation. That is your main operating frequency. The next part in this topic of op-amp are some of common applications. Constant gain amplifier. So you want to amplify a signal, you want to keep the same phase as the input, you will use an non-inverting. If you do not mind having a 180 phase shift, you can use inverting op-amp. Set the resistor for feedback and input in such a way that it will give you your desired gain. The second common type of application is controlled sources. We talked about 4 control sources. You can use op-amp circuits to make control current source, control voltage source, and the controlling parameter can be a voltage or current, which means there are 4 types. And filter. Just like any op-amp, for example BJT, you can have multiple stage amplifiers with op-amp. Every stage has its own gain depending on whether it's an inverting op-amp or a non-inverting op-amp. It has its own gain equation. When you connect multiple stages like this, where the output of the first stage is the input of the second stage, the output of the second stage is the input of the third stage, and so on. This is also called a cascade connection. A cascade is like a waterfall. A waterfall with so many floors. So the top floor, the water comes in, goes to the bottom one, and then goes to the bottom one, and it flows down. To calculate the gain of multiple stage amplifiers, you have to find the individual gain and multiply all of them. Again, it's not limited to 3 stages because of the space here. They provided only 3 stages. You can have more than that. We talked about control sources. You can have voltage source or current source controlled either by a current or a voltage. Nothing changes in the hardware of control sources. What has to change is the way you look at things, your perspective. Something is missing in the slide. This is missing, B1. You see, it's a non-inverting op-amp. For a non-inverting op-amp, you may or may not have this resistor, but what is used for calculating the gain? Only the feedback resistor connects with any other resistor. The feedback resistor is the one that calculates. So V out equals 1 plus RF over R1 times V1. Now, if you look at the equation, what if I write V out equals K V1? Can I write this? K times V1. RF is fixed, R1 is fixed, and 1 is a constant. So V out is K times V1. Means this is a voltage source. You will use this output voltage as a source to something else, but it is controlled by another input voltage V1. V out is a function of V1. Output is a function of an input voltage. That's why we call it the voltage control voltage source. Nothing really changed. We don't make any fundamental changes in the connection. Having an RC or not having an RC also doesn't matter, but it's a good practice to have a resistor in order to limit the input current. What was the first one? Non-inverting amplifier version. You can do a VCVS, which is voltage control voltage source, using an inverting op-amp. Inverting op-amp is quite straightforward. The non-inverting pin is on the ground. Inverting pin has the input. You have your input resistor and feedback resistor. Output equation is this. I can also say minus RF over R1 equals K. So V out equals KB1 again, satisfying the condition that now you have a source. This is a voltage source. You can treat this as a voltage source controlled by another input voltage V1. Let's say you want a variable input voltage which will go to the next stage of your circuit. So this one you can feed as a source to the next stage, and you can control the source using this V1 behind. That's the voltage controlled voltage source. Any questions or comments?
Not now for me.
We almost finished this review today. I don't know what to do in the next class. We have one more class. Or we should stop before the filter and then release you early. It depends on you. What do you prefer?
You mean next class?
Yeah, we have one more class before the midterm, one more Tuesday, because Thursday is the midterm. So we don't have class anymore on next Thursday. Today is Thursday, we have one more class. If we finish everything today, what will we do on the next class?
Can you like question like next class we doing the review question?
Review question?
Yeah, like in each chapter, like you bring the question to us.
I will ask question to you in the next class from all chapters, and you should be answering.
Like the problem solving.
Problem solving?
Yeah.
What type of question? Obviously, I cannot show you the exam question. So what type of question would you want?
Yeah, like
Similar? Similar
like in
question?
the Google, no, like in the Google, what is that called?
Quiz?
Oh yeah, class note.
Class note.
Wait a minute.
The one that we did in the class? Something
Yeah, the
like
class.
that?
Yeah, the question like in the class notebook like that you show us.
Oh yes, okay. Those are exercise problems.
Yeah, the exercise. I mean the exercise. Yes.
But you will have to do it, or you will have to tell me the different parts of the solution. I can ask so many things. For example, I can show you a diode circuit and ask what is the output? What is V out? What is current out? Or I can give you, for example, a Zener, clipper, clamper, etc. We can do some practice.
Yeah. Okay,
Yeah.
JB.
One class may not be sufficient for all the chapters, but nonetheless, I'll start from diode chapter and see how far we can take that.
Yeah. Thank you, teacher. Because some question I do not get it. Yeah, when we solving the exercise.
What of the rest of the class? Do you agree with this plan?
Yes.
Yes.
Sounds good. Okay, let's try to then quickly go through the rest of the op-amp. Voltage control current source. Now, instead of looking at the output from a voltage perspective, you can also think that I'm getting an output current. Because you have an input current, you have an output current. Sometimes you don't want to calculate the voltage, you just want to calculate the output current. Because instead of a voltage source, right now you're concerned about the value of current. You need specific amount of current for the circuit. So stop thinking about the voltage right now, you can start thinking about the current. Here's the equation. V plus equals V minus. V plus is 0, V minus has to be 0. So I1 is V1 minus 0 over R1, or V1 over R1. I out is same as I1, so I out equals V1 over R1, and V1 over R1, if I take 1 over R1 times V1, I can say it's KV1. Now you have a voltage controlled current source. You will change the value of the current by changing the voltage alone. And then you have what else? Current controlled voltage source. Anything left of the I1 is hidden, but actually there's a resistor R1 over there and input voltage V1. But since now you are forced to think in terms of input current, we call it the input current I1 coming in. V out is negative I1 RL because I1 equals I out, so I out is I1. Ohm's law, current times resistor is the voltage, but why negative? Because it's a negative pin. Look at the equation. Output voltage is K times input current. Current controlled voltage source. Now you want some output voltage, but you, instead of thinking about input voltage, you are thinking in terms of input current. How are you going to change I1? I1 is V in minus V minus divided by whatever resistance you have. There's R1 hidden. Here is an R1. If you change either R1 or if you change input voltage, you change I1. Same idea. Then you have current control current source. Here it is a current divider rule equation. Finally, it says that I out equals a constant times input current. We did some problems, maybe some were examples in the class. We did about, I gave you 2 or 3 circuits, I remember, and I asked you to find the output voltage and output current. Another op-amp common application is in instrumentation, driving a display, driving an instrumentation amplifier. This is how it works. This one, you see some circles with numbers. These are the pin numbers. Pin number 2 is inverting, pin 3 is non-inverting. On 8 and 4, pin numbers 8 and 4, these are, it's called V saturation, positive 1. So you provide the DC voltage here. The other one you can ground. Pin number 1 is the output. The number 358 in the middle, it refers to the model of the IC. It's called LM358 IC. I think the name of the company is Fairchild Semiconductor, one of the largest semiconductor manufacturers in the world. How does this display driver work? Here, when V plus, you have 2 different voltages. When V plus becomes greater than V minus, the output is high output. When there's a high output, you know what output will be from the op amp voltage. In terms of voltage, it will go saturation plus 5 volt, but you will also have 20 milliampere current, enough current to display on this LED. If V plus no longer greater than V minus, it will go to saturation low. Here the saturation low is 0 volt ground. Sometimes you might see -5. They put a -5, so it's -5. There is no, it is not forward bias anymore. The LED will not turn on. Here is 0 volt, no current. LED will also not turn on. This is how an op amp can be configured to run a display driver. The last thought application that we did in the class, active filters. If you connect op amp with resistor and capacitor, you have seen how it behaves. It can either work as an integrator or a differentiator, which will integrate or differentiate the input signal to give you a certain value of output. But adding RC, resistor and capacitor stages on the input side will also create filters, frequency filters. We mainly talked about 3, but I mentioned another one, band stop filter. We started with low pass and then high pass, band pass. If you change the configuration, the sequence of high pass and low pass, you will make it a band stop. What does a low pass filter do? What is it supposed to do? From the name, you can guess that the low frequency will pass, the high frequency will not pass. Let's say you have a signal that you want to pass through, and around the signal you have a lot of noisy signal. I should not say noisy signal, I should say noise. Unwanted signal. What type of filter you think is best? Is it low pass or high pass? You don't want the noise.
Low pass?
Low pass is a good one. It's the most common one because typically your signal goes like this, so pretty steady. Most of the noises are actually high frequency noise. It goes like this. Most of the noise signals that I used to study about and work with, they are high frequency noises. So you want the low frequency to pass and the high frequency to, you want to kick it out. In case where you have a lot of possibilities for high frequency noise, like a vibration, you can use low pass filter. I personally have not worked with any low frequency noise, so I don't know. Maybe there is. So first with the input, you will connect resistor first and then capacitor. Capacitor goes to the ground. Output is, in real life, the output does not drop exactly at the cutoff frequency. It will slowly decrease. So the gain becomes less and the noise has no chance to amplify. There is a equation to calculate 1/2 pi R1 C1 to calculate the cutoff frequency. A V, I don't think this is quite right. I think it should be 1 plus RF over RG. Because when you have a non-inverting pin, we have seen that the ones that are connected to the inverting pin are used for gain calculation. Please double check this one. I have a doubt about this one. Anyways, so how will you use the R values? To calculate the cutoff frequency 1 over 2 pi R1C1, refer to the resistor that is connected with the input and the capacitor. Do not use the resistors which are grounded and not part of the input to calculate the cutoff frequency, but the gain calculation should be according to your regular derivation. If you want this cutoff frequency, if you want the high frequency signal to fall off even more rapidly, not slowly like this, you can make the slope negative 40 decibel per decade. It goes down by 40 decibel per each 10 times increase in frequency. How do you do that? You can actually add another RC stage. This is for negative 40. We call this the second order. So you have V1, R1, C1. This is a peculiar connection. It goes on the output. Then you have R2, C2. After the first stage, it has to pass through the first stage in the beginning. After the first stage, when it goes with the second stage of R2, C2, it will fall even steeper. You can make even better like this. You have R3, C3. For a high pass filter, the low frequency does not or is not supposed to pass, only the high frequency. Theoretically, you want this low, and then you have low cutoff, and then you have the output. This in the ideal fantasy world. In reality, you will see the effect gradually happening. So your cutoff frequency is 1 over 2 pi R1 C1. What is the difference of arrangement of capacitor and resistor between high pass and low pass? For low pass filter, resistor comes first, capacitor is grounded. For the low pass filter, capacitor comes first. Sorry, high pass filter, capacitor comes first, the resistor comes second. Again, in this formula, this equation, you concern yourself only with the resistor and capacitor that is part of the input. The upper part does not come with the input. The upper part is not calculated. If you combine two types of filters, low pass, high pass, you can either get band pass or band stop. In a band pass filter, you want, what do you want? A certain band to appear on the output. So it's like this. And then after this band, nothing else appears. Before doesn't go through and after doesn't go through. If you divide this part into two small parts, the first one is what? High pass filter. The low pass doesn't come in, the low frequency, the high frequency comes in. Here you have what? A low pass filter. The lower part comes in, it becomes very high, it does not go anymore. So this is LPF, low pass filter. This side is high pass filter. For high pass filter, we call the cutoff frequency a lower cutoff frequency. And for the low pass filter, it's just the opposite. We call the cutoff frequency as higher cutoff frequency because it becomes too high for the low pass. And for high pass, this one becomes too low. What if I change the arrangement? What happens if I put the low pass in the beginning? Here, see, stage 1, stage 2. Stage 1, you have a low pass. High pass, capacitor first, resistor the next one. Stage 2, you have a low pass, resistor first and capacitor on the ground. If I flip, if I make the second stage the first and first stage the second, what kind of output waveform do you expect?
Can you repeat the question?
If you change the arrangement. Now you have high pass as stage 1 and you have low pass as stage 2. If I make stage 1 a low pass filter and stage 2 a high pass filter and combine them together, 1 and then 2, what kind of output would you expect finally?
Maybe the noise will be reduced at first and will be increased later.
Well, that is not answering the question that is being asked. The question is, what will be the output waveform? The output graph. Okay, if you don't understand waveform, the output graph, what will it look like?
It will dip down first from the low pass and then rise to the high pass.
Dip down. Okay, can I draw? Let me try to draw this. Say it will dip down like this.
Yes, and then it will rise at the high pass.
So what is happening? What is happening if you see this is the x-axis, this one the y-axis. Let me try to make shadow or shading, whatever you call it. This is the opposite of band pass. This band is passing. What is happening between this zone and this zone? There is a frequency band. It does not pass. Anything before that will pass. Anything after that will pass. This band is getting blocked. If you have a bandwidth from this to this signal will not be passed through. It is called a band stop or a band reject filter. Band stop is the opposite of band pass. You want a certain band to pass, you use high pass and then low pass. If you want certain band to not pass and you don't mind the rest, this is what you use. You have to use low pass section first and then high pass. It will become a band stop or band reject. I think there's a third name for it, I can't remember. So that is the end for the review of all the topics. It's almost 2:40. I will not start the problem solving today. In the next class, which is only one class left, the exercise problems in the class, I will again try to revise, do the review with you. I'm just looking quickly what are the exercise problems from op-amp. You have a class notebook. It's loading on my computer. You don't see it on my screen. We have content library and then we have collaboration space. We have been working through the collaboration space. Yeah, there are quite a few. Let me switch the screen for a moment. Here is one of the examples we did for op-amp. Calculation of common mode. This is your main equation of the op-amp, ADVD plus ACVC. So given in the differential mode, you can see it's a differential mode, it says VD. How you calculate VD? V plus minus V minus. So half minus minus half, you have 1 millivolt, you have 8 volt on the output. What is the differential? VD is 1 millivolt. What is differential gain? Output divided by input, 8,000. And then shows the common mode. It says VC because it shows an arrow for transformation. It says VD is 1 millivolt. VC, you can see 2 millivolt, 1 plus 1, 2 divided by 2. Common mode is like this. And what is common mode gain? Output divided by input, you have 12. Differential mode gain is 8,000, common mode gain is 12. When you all put the values and add, you have the output voltage of 8.012. See, differential output is 8 volt. So where is this 0.012 volt coming from? It is the result of operation in the common mode. Only a tiny portion of your output volt is coming from the common mode. If you take, for example, 8.012, no, 8 divided by 8.012, what will you get? 8 divided by 8.012. 99% of the output, 99.8% of the output is due to the differential mode. 0.2% is due to any noise or common signal. It's a very good filter actually. See, the ratio alone is 667 about, and in decibel it is 56.5 about. Not a bad one. Also remember, you can express the output just like this equation. AdVd times 1 plus 1 over CMRR and then Vc over Vd. It's just a derivation, nothing else. We talked about an example 1022. Determine the output of an op-amp. You're given input voltages of 2 pins, given the differential gain, common mode gain is not given. So you have to use that equation. Vout equals AdVd plus AdVd times this thing. You can find the differential voltage using V plus minus V minus, and then common mode by you adding them, divide by 2. This thing should be a plus sign, so there's a mistake here. We did problems with filters, low pass filter. Calculate the cutoff frequency of the first order low pass filter. So straightforward, 1 over 2 pi R1 C1. R1 and C1 values given. You get 6.63 kilohertz. We did a high pass filter. 1 over 2 pi R1 C1. Typically, if you have multi-stage, the R values and C values, they are the same. Even for the second stage, the formula remains the same. And then we had a band pass. You have a high pass and then low pass. Calculate the cutoff frequency. We did calculate using 1 over 2 pi R1 C1 for the low pass section, 1 over 2 pi R2 C2. Don't use RG, RF or R1, R2. For this stage, you'll use the input capacitor and input resistor. This one resulted in a band. Lower cutoff frequency is 159 Hertz and the higher cutoff frequency at about 8 kilohertz. All right, so let me take your attendance. You can come prepared in the next class for doing some exercises. Today is January the 6th. Balan, Is Balang here? Tirawut?
Yes.
Napatra?
Yes.
Pakong?
Yes.
Rajay?
Yes, Achan.
Jonikam?
yes ค่ะอาจารย์
Michelle?
yes ค่ะ
Phil?
Yeah, here, sir.
Silicon?
yes อาจารย์
Wisalut?
Yes ครับ
Yu Cheng? Mr. Yu Cheng?
Yes, teacher. Yes, you can.
Okay. Shesehang?
Yes อาจารย์
Patampong?
ครับ
Kongsu?
Yes อาจารย์
Martin?
Yes อาจารย์
Kolawit? Is Kolawit present? Pichayut? Did you see your quiz course? I posted the quiz course. Is Pichayut here? No. Pichayut is not here. Today is absent. Your quiz score was posted this morning on your Microsoft Teams. Jima?
SQB อาจารย์
Yes, I'm here.
Suanyuan?
Yes, I'm here.
Satawat?
Yes อาจารย์
Yapeng?
Yes, teacher.
Seni?
Yes, present.
Siripop?
present อาจารย์
Vitu?
Yes, I'm here.
Sanan?
Yes
Waramet?
Yes.
Nabawan?
yes
Natapop?
Yes I'm here
Warapat?
Yes.
Nataya?
yes teacher
Ichayapon?
Does she go to toilet อาจารย์
Okay. Komchan?
Komshan teacher.
Iradon?
Yes, I'm here.
Kitsanapong?
I'm here, teacher.
Aditya?
Yes
Tasin?
yes
Sukaina?
yes
Siri? Sirin? Minluin U? Okay, attendance is closed. See you on next Tuesday.
Okay, thank you, sir.
Thank you อาจารย์
Welcome.